This
Am I
meeting
audible?
is being recorded.
Professor,
Okay.
audible? Yeah, you can. You may please start, Professor.
I think the presentation is also in full screen mode, I guess.
Yes, yes, it's clear. Good to go.
Okay. So let me just take this out. Okay, so good evening. I think most of you had a good introduction to quantum mechanics and some aspects of hardware and quantum materials over last 2 days lectures. So I will try to just give a good generic introduction so that we can recap few things and see why quantum computation really matters, both on a mathematical sense and also on a physical side. Like what is it to offer us in long run? So, introduction and scope of quantum computation is a very broad topic, but I will try to just give a big overview for first 40 to 45 minutes, and then the remaining 1 hour, 15 minutes or something, some specific examples and how we really do operations and how quantum computation programmings are done using circuits. So that's just a big picture. So let's see. Actually, okay. Let's here. Okay. So we all know how things don't happen overnight. It might look like things are dramatically changing, but in reality, everything takes a lot of time, a lot of hard work, and a lot of big or bold moves. So the history of computers, if we go back and recall when people were building first version of classical computers, which we are using today at to the full its fullest capacities. Nobody thought that it's going to be so widely used. In fact, it was said that might be three, four, five computers would be sufficient enough for the need, and that was their target. But people started learning to use, people started learning to make multiple ways for them to, make it usable or, okay, people came up with various ways to use them efficiently for our daily life. Right? Today, including our social well-being also is sometimes handled using computers. So first generation was really a very big machine, which was almost about 30 tons, and then
Professor, sorry to interrupt you.
Yeah.
So there is a message in the Q&A. Can you please look into it? They say
Okay.
something about the presenter mode.
Is it okay? So how do you see it?
For me, it's fine.
Slideshow.
Yeah, it's fine. Go ahead, Professor. Sorry.
Okay. Okay. So in the first version of computers had a lot of vacuum tubes, and the way it was almost a two-story, two-floor big rooms in University of Berkeley. And then with the invention of transistors, vacuum tubes were gotten rid of, and that again took almost 20 years of a lot of research, and people could actually bring it down to a very reasonable compact form. Programming languages were developed. So programming languages initially were very crude, and then they got refined, and people have started, writing codes and then running them on the computers, and they started seeing things which is not easily doable in standard manual ways. And then today we have integrated circuit which has come up, and we have a very compact version of processors doing wonders for us. So we do think, we have supercomputers. It can do a lot of calculations which can't be normally done, but that those are all true. But then if we go back and see how our computers work, these all work on mathematics. These are binaries, right? Classical bits, zeros and ones. Even if I ask the computers to do a calculation of 2 plus 2, it converts it into binary and then gives us a result. And again, it converts it back to me as a numerics or in the order of what we regularly use, like it gives me 4. And any hard calculations or whatever I do, it converts into binary and look at it, right? So every information is stored as a sequence of binary. So it is largely driven by a mathematical binary language. So that's how our computers works, and they're doing with it. But what one of the earliest thesis, what we call the church Turing thesis, proposed at that time was that if I have any function which I think are computable, right? It means that if you think anything is in a simple language, if you think there's anything which is calculable, then a universal Turing machine, what we call as a universal computer, should be able to do. So that's what he said. And that was actually kind of invitation for people to come up with functions and algorithms so that you can use computers and then solve them. So people started thinking of simple problem to big problems, or what we call as a functions, and see how you can write programs for it and solve them. And that does serve as a basis for computation language or a classical computers which has been built. But what I would like to try to focus here is, though we have a huge computational power, and then we say that we have the supercomputers, but still they can't do many things. a lot of things, right? I will just try to go take up some simple examples to see what are those many things which they can't do, and that does surprise us, right? So it's an optimization problem. So when I say optimization, I'll give you some examples, just some simple examples. Now you just see this plot. This is a very a simple factorial growth of n from n is equal to 0 to n is equal to. We might, you might know what you mean by factorial. I'll not go into the detail of it, but it was kind of we can map it into a real life problem. You will have an auditorium or probably a classroom, and there's a lot of seats available there. And what are the possible combinations for people or student to sit in a classroom? It looks like a simple problem, but now if you start looking at the number of ways they can sit with increasing number of people and or number of seats, and it just grows exponentially. So you can see here there it's going 3.5 followed to 10 to the power of 6, right? It's a huge number of possibilities. Now, in that, if you want to see, there's one particular solution. There is one particular combination of seating arrangement, which is of interest to you. And you need to find out that particular combination. Then that's a quite hard problem, an optimization problem. So the way you try to map them as a computation problem is that you treat that as some minimum value or solution, and you try to see how quickly you can reach to that. And if the number goes into hundreds, that's thanks to the computers, they can't solve, right? The best of supercomputers can't optimize them. There's another simple problem. There's a graph theory problem, which we call graph coloring problem. This looks like very simple. I know there is an arbitrary graph. Now, if you see here, you have to color the vertices such that, or the edges such that the neighboring edges don't have the same color. Right now, given a graph structure, what is the minimum number of colors you would need, and how do you color them? Right. So now that is a big problem. So optimization is what is the minimum number of colors you would need for a given graph structure. That's not an easy problem. I know if I have, if I have 100 nodes and if I have 100 colors, then it's fine. But if I have to optimize the number of colors I would need, I'd say, okay, this is the final answer. I need a minimum of this number of colors for this answer. So it's not an easy problem. And computers, the best of computers, could take ages to solve them, particularly if graph becomes very, very complicated, or if it's a complicated structure, then you can't still solve them. So this has nothing to do with nature or natural way. These are just simple mathematical problems. It looks very simple, but very hard to be solved. So like that, there are other examples, right? These are the two examples from a mathematical side I gave to see why our existing computers are not still enough for us to solve hard problems. But there are other interesting problems which have to do with nature, right? So something which is in a chemistry, right? This simple chemistry problem. It looks like a simple one because we all today, no, I think nitrogenesis might be some of you might be familiar with. That's the way where your fertilizers are converted in the nature to so that there are some particular reactions and fertilizers works on your food crops and you get better yield. And people have been working for years to find out what is the best configuration so that you have an efficient fertilizers and optimal fertilizers for your food crop or food produce, right? So there are nitrogenesis enzymes and that involve nitrogen and NH reactions. I mean, you don't have to worry about chemical details, and I don't bother too much about it. But what interests me here is the structure and the reactions. If I try to model those reactions, I need to write a program. And if I have to write a program, then I need to take to account the electrons configuration in nitrogen and all those chemical complexes and try to see how they react. So the computational power needed to find out an exact reaction configuration or what configuration reacts better way is a very hard problem. So there is an example here. There is one cluster. You can just take this one particular point you can see in the screen, F cluster. And there are multiple clusters in this such kind of proteins where these reactions happen. And the best of the classical computers today can't simulate can simulate F cluster, but they can't simulate P or M clusters with that. So because the computational power needed for them is very, very high, and because they don't have enough computational power, they parallelize it, break it down, and do some approximations and come up with an approximation configuration of some chemical complexes which are useful. So there again, our existing computational power fails to give us exact answer, and we have to deal with approximations due to the limited power. So this is to do with again the possibilities for the reactions to happen, and the way they interact with different degrees of freedom of what we call interaction power, right? So those things makes this problem very, very complicated. So again, this is another example from the chemistry side. Now there is another very interesting example which biologists and chemists have been trying to understand from a nature's perspective. They have tried to see some molecules or what we call algae, right? This is a complex which defines an algae. So they have found some algae which efficiently convert light falling on them into an energy. So you can see here a schematic here where there is light falls onto them and then it takes a particular route, gets into the reaction center and converts it efficiently into energy. So now this is what happens in photosynthesis. Light falls into the leaf and light is convert. There's photosynthesis. It converts into energy, and then the food supply chain for the plants works. But the problem here is the modeling of such kind of dynamics has been very hard. People have been trying to model with various approximations, and they have not been efficiently be able to model. But nature does it much more efficiently. So what I have figured out is there are certain algae which are deep inside sea, and they get very, very low light, very few photons in a few days, and they efficiently convert them into energy and then survive. So which means that their efficiency rates are more than 98%, and that surprised the academic community. So which means that there is some dynamical process which is happening which we don't understand and we can't model. And if we learn that kind of dynamics, and if we try to mimic them by artificially synthesizing them, then we can have highly efficient solar cells built. And that's something which revolutionize our energy power. We don't have to deal with losses. The best solar cells today are about 20% efficient, or close to 30% efficient, right? That's laboratory level. Commercials are much more low efficient. So now this is not a complicated problem in the scale wise, like in the previous one or in the optimization problem I was telling, the number of possibilities goes exponentially high and then finding out the solution is difficult. Here, it is not just the number of possibilities. It's the number of possibilities might be very small here, what path it can take. If you see here, there's a schematic, what path it will take, but how nature is controlling that dynamics. So it means that there is something to do with nature. It's not just with the math of zeros and ones and how we can calculate with it. So there is a nature's law which is defining the dynamics, and we need to understand them. So to understand nature's law, what should we do? We need to mimic the nature the way it is done, right? So now that's one of the other ways why quantum computers or quantum mechanics comes in this picture, right? And this is another example which I tried to give. So to sum up, the kind of problems we have, there are what we call the complexity zoo or the zoo of problems. So there are problems which we can solve in polynomial time. There are problems which are completely what we call non-deterministic in polynomial, which means that we will not be able to solve them in polynomial time. And there are problems which are non-deterministic polynomial, and they are quite hard. You can do one way, for example, factoring, right? If I'm giving you two numbers, then I can always multiply them and give you what it is, right? But then if I'm trying to ask you to do the reverse way, you can't factor the large numbers with the right factoring values, right? So that's a computationally hard problem. So there are various class of problems which can't be solved, like NP and NP complete problems are a huge class of problems which today's existing computers can't solve them. Right? So we know that the existing power does not allow. It can only solve a class of problems which are polynomially deterministic, or you can solve in polynomial time. And now that makes that the sample of problems which you can solve very small, and the class of problems which you can't solve are very, very large. So people have been working on developing algorithms to efficient algorithms to identify what kind of problems can be solved or can it ever be solved. So that's been a continued research. But can there be a novel way of doing computation to solve the problem is another question which people have been looking at. Factoring, I gave an example, is because quantum computers are one which can actually solve factoring problem very efficiently. And that's one of the reasons I went. And then there are a few other classes of problems which quantum computers can do that the normal computers. So to sum up from the examples, there are quite a few examples, or few examples which is mathematically oriented, or from the chemistry side, or a natural nature's way of working. So if we take them all, there is various reasons for us to think of building computers, and why quantum computers is what I've titled here, but a computers which is far better than what we have today. There are many reasons. So why quantum computers? The reason is simply being here. I know these are the points which we always uh, see as a guiding line. Science evolves, our understanding evolves. Newton's laws of nature, or Newton's laws explains nature very efficiently. We still have cars running on roads without colliding, flights on air travel without colliding, and they all are very well defined by Newtonian physics. But the moment the speed gets closer to speed of light, Newtonian physics starts saying its limitations. We need to, get to Einsteinian physics, what we call relativistic quantum mechanics. So only when we have relativistic quantum mechanics, we can predict what nature does efficiently. So what we can understand from that is that with certain approximations or with certain limitations, things work very fine. But then if you want to get to very finer details, or if you want to get to speeds of very high, then Newtonian physics doesn't work well. We need to start using Einsteinian physics, what we call relativity theory. So there is another way of looking at it. Everything at a macroscopic level. I play cricket, we throw ball, and we can always see the trajectories and everything well. But the moment you go to an atomic scale, atoms don't behave like a cricket ball, or atoms don't behave like any macroscopic elements. They have their own laws to define. Only when they become bulkier, their atomic behavior becomes insignificant, but we start looking at them as a macroscopic object. So the laws which defines atoms at the very elementary level are not from the classical physics, right? We have to invoke quantum mechanics. So that's where we call classical physics is a good approximation of quantum mechanics, and Newtonian physics is a good approximation of relativity or Einstein's physics. In a similar way, the information, what initially I said was binaries and zeros and ones, right? The way we encode information, the way we extract is a classical information, is what we call them today. It's a good approximation of quantum information. Why does quantum come in here? Because if nature's laws are defined by quantum mechanics, then the information from nature should also be a quantum information. So then the classical information should be an approximation of quantum information. So that's what motivates researchers to see. In all these cases, we have to get rid of approximations and get to a more precision to understand information from a quantum mechanics language, or understand atoms from a quantum mechanics language, or the way dynamics happens at the speed of light from relativistic language. So, but what happens is the moment we start going deeper into it and understand them with very minimal approximations, a new knowledge comes into our existence, and a new technology is getting developed. So that's how it is, all right. With nature, we are beginning to understand them, and we are building up the technology around it. So, in a nutshell, we see relativity in that we remove the approximations that we are traveling at much smaller than speed of light. So if we consider that we are traveling at smaller than speed, much lower than speed of light, Newtonian laws works. But if we try to take speed of light, then relativity works. Similarly, quantum mechanics, in that we remove the approximation that we are manipulating things at much larger than atoms. We have to start thinking that we are manipulating things at atomic level. Then quantum mechanics explains things very well. Exactly in the similar way, quantum computation, we remove that approximation that elements of information are independently manipulable. But that's something which is a bigger picture. But what um, really drew attention of a lot of physicists is Feynman's statement. And now this also tries to, we can go back to one of the earlier slides where I was talking about photosynthesis problems. If nature is doing something, if we are to understand the way nature does, then we need to mimic them explicitly. If I have to mimic them, then I need to use the same language which nature does. If I'm using some other language, then I'll be doing approximation. So that's exactly is what Feynman was saying. If I'm using a classical computer, which is just a mathematical language, is binary, to simulate something which is physical in nature, then I'm already, missing out something there. So I will not be able to mimic it exactly the way nature does. So the moment you're missing out, then you will not be able to model them efficiently. And that's what was this opening, that was opening to the era of quantum computing. So in 1981, in his speech, he said that, I'm not happy with all the analysis that goes with just the classical theory because nature is not classical. And if you want to simulate nature, you need to build a machine which are, based on the principles of quantum mechanics. And that's what quantum computers is all about. And again, there is a computer science perspective for the same thing. A computing machine which resembles universal quantum computer could in principle be built, and we would have many remarkable properties not reproducible by any Turing machine or complexity theory, which deserves further investigations. You may recall that there's a Turing thesis which I said if there's any function, if we can solve that function, if you think we can solve that function, then we should be able to do it with classical computers. Now, what David Deutsch, one of the other founding fathers of quantum computing, is what we can call, said that if you can build a computer using quantum theory, then you should also be able to solve a complexity theory which can't be done by just a standard Turing machine. And that's again was an invitation for people who are working from computer science community to take up quantum computers a bit more seriously. So if you say Feynman statements motivates most of the physicists to see the topic as a big invitation to explore nature, and David Deutsch statements is again a motivation for people working in mathematics and complexity theories, computer science to explore quantum computers for further investigations. That's how it all started in 1980s, and there was algorithms which really showed the practical value of quantum theory or playing role in quantum computation. So it just gives quantum algorithms, right? So there are simple ways to define. I'm giving some simple example. This is one of the biggest, I should say, one of the very early breakthrough papers, which really made every government to think about it. So the governments across the world did worry too much about Feynman's statement or David Deutsch's statement. They said, okay, the researchers keep asking questions and they find solutions. But Peter showed that you can, if you have a quantum computers, you can factor numbers very efficiently. Right? So if I'm giving there's just a factoring problem where n is equal to pq, and if the question is find p and q, right, a best class, if the number is very large, like 20, 200, 300 digit number, then the best classical computers will take 2 to the power of the order of n to the power of 1 by 2. So that's a large, where n is the number of digits. So the time needed would be very, very large. And keeping that as a benchmark, people have developed a lot of cryptography algorithms. So there's a standard RSA cryptography and few things where people can, security keys are based on this P and Qs. So they thought, okay, computational power required is very, very high. The runtime needed is very, very high. So people can't easily factor and get the solution. So information is secure. It was a just standard understanding. But what Peter showed like this, what it says, like today's fastest classical computers can factor this number with approximately 100 to 200 digit, and beyond that it can do. But what Peter showed in 1994 was, if I have a quantum computer, he said, I'll tell what are the basic postulates of quantum mechanics, which makes it faster later. But you can see the figures here, order of n by 1 by root 2 over 2 to the point, that is just n square, order of n square. So I said it can factor number very fast, and that really scares anybody who are working in cryptography or security ensuring agencies, because their secret keys can be hacked if somebody has quantum computers. So that's when the governments thought it's very important to look at it. There's another interesting algorithm which was developed at the same time, which is called Grover search algorithm. And this is a very simple example that I have a used database and how efficiently I can find, right? So now there's a mathematical protocol which I've listed down with few steps, but you can keep them all ignored. But let's think about a telephone directories. Some of you may not be familiar with it, but the older generation knows them very well. The telephones directories were given to everybody who owns telephone in a city. That was everywhere in the world. They had this problem, or they were using telephones, and there were names listed in alphabetical order, and then the numbers associated. So if you know the name, then you can actually go and search for the telephone, and you can call the person. That was before the mobile era. So now these are all a sorted database. So which means that there is a sorting in related to name, and then you have to figure out. But if I give an unsorted database and you ask you to find out, please go and get me the number of so and so person, or you just pick this number, then which means that you really have to go and check every name in that, and then you may find. On an average, you need to search at least half of yours. So the worst case scenario is that you need to search the whole directory. The name you were looking for or the number you are looking for might be at the last. Rarely you might be lucky that it might be in the beginning, but on average, you need to get, at least scan half of the number of the directory. But what quantum mechanics says was that you don't have to go and check every, name in one after the other. You can simultaneously explore the multiple names. So that simultaneous exploration comes from the principles of quantum mechanics. Again, postulates of quantum mechanics. I'll describe them in more detail, but you would have had that introduction to that in earlier lectures also. It's called superposition. But what Grover showed was that if I have a quantum physics-based mechanism, then I can search with root n queries, so which means that you are getting quadratically fast. So quadratically fast search is something which was again one of the best algorithms for searches at that time, and people thought, okay, this is another very useful thing which can happen if we can build quantum computers and then use it. So there are various algorithms which have been developed based on later on. People have been continuously developing. There's another algorithm which simply helps in modeling various dynamics in nature. For example, you might all have heard about a random walk problem, where tossing a coin is a very common thing for us. I mean, we toss a coin, you get head or tail. You say if it's head, you go to the right, tail, you move to the left. Now, this is again one of the search algorithms. And how do we find the information which we want? I it was with an unbiased way, I need to start my search. Then instead of telling that, let me go and search here, I'll toss a coin. Let's say I'll go to this direction, search, go to some other. So you can continuously keep looking at it, and there are some chances of you getting where you want. But a quant, and that's not only helping us to search, That has helped us to model dynamics in nature. Today, there are a lot of statistical physics problems or condensed matter problems where dynamics of atoms, dynamics of biological molecules or biophysical systems are all modeled using random walks. It is called, people make complicated higher dimensions, people make complicated ways of describing and then try to simulate something which is happening in nature pretty efficiently. A similar thing can be looked for the quantum walk, where instead of tossing a coin and going to left and right, because quantum mechanics allows us to simultaneously explore multiple paths. So you can see in this pictorial image that there are two. One, the first top one is a classical version, where you toss a coin, go to the left and right. You may not find what you want, but if you are using quantum mechanical principles of superposition, then you can end up finding the particle or whatever you want. And this is, here is a monkey which is looking for banana, but you can look for information, you can look for anything. That be done very efficiently. So what's it called? Okay, so there is just a simulation here which shows. I'm seeing, see if I can run. Okay, so there's some issue with the animation, but I think let's say, okay, so what it, if you see here the spread, which says that the one on the top spreads like a Gaussian distribution, but the one which uses quantum mechanical principle spreads much more wider. So which means that it can actually search for the space far beyond your origin, whereas the classical method stops within that range and it will not be able to search beyond that for a given time. So that's how we can see the quantum speed up which comes quadratically. It can be for search or it can be for modeling or various other systems. So there is, this is a very scaling examples which we try to see with from the quantum mechanical advantages, where whenever we see n number of possibilities, so quantum mechanics scales up as 2 to the power of n, and then the quadratic speed up. So when I say there's a quadratic speed up, or when I say exponential speed up, so you can see these two things, right? If there is n, the quadratic speed up, if n square, and you can immediately see how easily you can search for things. If there is any 2 to the power of n possibility, there are some algorithms which can do that, or some other applications where you can add this possibility, then this will be the one. So if you see, you can see how the classical will behave and how the scaling would look like. Just to say, so over a period of time, this is again a revisit of our class of problems which have been looked into. Classical computers solves most of these polynomial time solvable problems very efficiently, but there are quite a few algorithms which have been developed using principles of quantum mechanics, which can solve problems far beyond what classical computers do, which we call as bounded in quantum. They are bounded quantum polynomials, which means that the definition of polynomial, the problem solvable in polynomial time, gets extended the moment you start using quantum mechanics, right? So this is a bit shaded line is that this is an evolving goalpost. So it's not fixed. New algorithms keep stretching the boundaries, and the problems are getting added into that on a regular basis. So it's an open field, is what we could call. Okay, so now let's go into a practical scenario. Those are all like what are the possibilities of quantum mechanics, what they can do very efficiently, or what they can do beyond what classical computers do. But realizing them is not an easy task. Of course, Einstein's invitation or David Deutsch's invitations are like very welcoming. Mathematically, we can see them; they are very, very promising. But the crux of the problem would be, how do I build a system which are given by principles of quantum mechanics? So, because there is some point where I said, what do we mean by quantum mechanical principles? Where do they show up predominantly? It's at atomic scale. So which means that I need to handle control atoms, or I need to control subatomic particle at that level, very efficiently to do computation. So that's not an easy task, right? So this is just an example of one of the hardwares which people have built. It's an ion trap processor output with about 53 qubits in it. I'll explain that. So there's a huge effort which has gone into. This is try to say the technology roadmap from the very weird description of nature, where a lot of scientists did not even believe that uh, there's something which is missing. Quantum theory may not be the most ideal description because they thought many things were missing in them. But from 1900 to 1980s, a lot of theory were developed, and people tried to convince themselves that yes, quantum mechanics is true, or there is this weird way. At that time, it was called weird. Now we had call it as a normal way, because which period we start accepting the way nature behaves, right? So the way the atom or photons interact was all very well defined. But only in 1980s, people started experimentally verifying some of the fundamental theories of quantum mechanics. And only over like last 2 decades, we've been able to engineer quantum states. So there's a huge difference from observing and understanding and doing elementary experiments to engineering. So it's engineering, which means that I should be able to control the subatomic particle in the desired way. So that's when I can do computation, right? So people started looking at manipulating atoms at a single atom level, or photons, controlling photons at a single photon level, controlling spins of an electrons the way you want at a single electron level. So that started from 1990s, 2000, and that's kind of now as getting itself taken up, moving forward in a very taking a big leap from around 2020 onwards. We can see that there has been a big push towards achieving something which no best classical computers can do. So what you call as quantum supremacy. So there is going to be a next 30, 40, 50 years, a lot of research, development of technology, which can change the way we do. It's not because somebody is forced to. These are all defined by nature, right? So almost all discoveries for us has happened in the same way. Electromagnetic theory, when it was understood, then people started, manipulating what we call engineering electromagnetic waves, and use it for various applications, including the wireless technologies which we have today. In a similar way, there's quantum principles which we have learned, which we are trying to understand, and now we can engineer them. The moment you can engineer them, then there can be a lot of possibilities of developing technology. Computing is one of them. So we see there's a lot of opportunities for next few decades to come up with various technology development and advancement with it. So why quantum computer speeds up? Why we can think of solving problems which cannot be done? This is a simple example to talk about computational power, which we are going to get. Right? This can be seen in multiple ways. But let's give a very simple picture for it. We all know atoms consist of nucleus and then electrons. So electrons have orbits, it's ground state. It can also be excited into higher energy levels, and you can also kick them out of an atom and make it an ion or a charged atom. Right? But if I am carefully exciting electron from one energy level to another energy level, then there's possibility of an electron being at any of those two places, right? So I can treat them as two energy levels. So if I have to write a classical program to define those possibility, I need to treat binary. The 0 and 1 are the possibilities. But what quantum mechanics says is that you can actually have them in superposition, possibility of both 0 and 1 simultaneously, because I can make the electron be at the ground state, go to excited, come down, continuously revolve around, and bring it into superposition state. Now, if I have two atoms and if I have two electrons which I can control, and now the electron can actually go interact with the next atom, and then there can be four possibilities. So here, zeros and ones can be treated as both the electrons being in ground state, both the electrons being in excited state and one being in ground and other being in excited. So these are four possibilities I'm going to get. So with two atoms and two electrons, I'll get four possibilities. A similar way, if I end up having 3, 4, 5, 10, now if you see the numbers, how it increases, right? If I have only one atom and electron being in ground and excited state, there's two possibilities of describing. If I have two atoms and two electrons, which can go to ground and I have four possibilities. If I have three, then I have eight possibilities. If I have 10, I have 1024 possibilities. Now, if I have 2 to the power of 30, I have this 10 to the power of, 0 point or 10 to the power of 9 possibilities here, right? So now if you see, if I have 50 atoms and the possible configuration or the possible way of looking at them, I would end up having the power of 16 possibilities, right? That's a huge number. Now, that possibility, if I'm trying to map it into the number of bits available in our best of classical computers, then that's where we are stopping, right? So the best of supercomputers today have only the 10 to the power of some 16 bits of that information. So it means that even just to define an atom or a big molecule, let's say now I'll convert this to a molecule. I consider a big molecule which has 50 atoms which are interacting them, and that too interaction is happening only with one electron of each atom and the rest of the electrons keep quiet. Even at that limited, description, the just to define a problem, I need all the bits available, the best of supercomputers. Now that is where quantum mechanics can come into big rescue for us. What quantum mechanics would say, instead of just having binaries, I can have them in superposition. So it means that I take some other molecule which has all those possible configurations naturally, then I can mimic this molecule very efficiently. How I should control and all of them, there's the difficulties, but let's keep that aside. But what it says is that if I take one quantum system and then if I try to mimic, I can do that with very efficiently, unlike doing it with classical computers. So which means if I had to mimic a 50 atoms molecule fully efficiently, I need the best of supercomputers today. And beyond that, the best of supercomputers are going to fail. But let's look at it, an inverse problem. If I have a 50 atom together behaving like a computer, then what all it can do, the possibilities. If I have 100 atom which can behave like which in which I can manipulate or control energy levels of where it's going to be and how they interact and all of those things, then I can have a possible configuration which is far beyond what we are seeing here of 10 to the power of 16, which means it's crossing the best of the supercomputer's limit. So what this is trying to tell us is that if I can build a 50 to 60 atoms quantum computer or something equivalent to that, then I am already close to the best of supercomputers today. And that's how the number plays a role here, that 2 to the power of n, which comes from the quantum possibilities. That's, you can see the classical numbers matching there. That's where people see there's a big advantage of qubits, what we define now has plays a very important role. And these are some of the examples, right? For example, if I had to simulate a water molecule, H2O, the number of classical bits needed, because the possible configurations for hydrogen and oxygen to interact and look at it is 10 to the power of 4. The number of quantum bits needed is just 14. So now if you see ethanol, acetone, caffeine, that's coffee, sucrose, that's your sugar, penicillin, all the number of classical bits needed. And also even here the number C, if you see how difficult it starts becoming, right? Even to simulate the caffeine, the coffee which we drink every day, the classical computers have limitations to the very best of its capacity. So how do people solve those problems? They break them into smaller pieces and then study them and put them together. and there are a lot of approximation which goes into. So if I can build a good few hundred qubits quantum computers, there is a lot of problems like this which I can solve, which is a difficult task, but which does say the possibility of simulating things which are very hard to be done. And this other way to look at is that every time I am increasing, this is classical and a quantum computer, the potential power of computers doubles every time. You have to double the number of transistors in a classical computer because that's binary, right? You have to increase the numbers, you need to increase the number of transistors. But what quantum mechanics says that the possibilities is that if I add one additional qubit, then the power doubles. So if I have to double the power, I don't have to double the number of qubits because it's 2 to the power of n possibility, n, right? So it means that I just add one extra qubit, then the potential computational power doubles. So that's why, when I say I have 50 qubits quantum processor, its power is almost equivalent to the best of classical computers. If I have 51, the power would be again double that. 52 will be double of what 51 computers would do. And now that's something which is remarkable. That's what makes it very efficient. And coming to the possibilities, they're still very hard. People have been exploring various potential hardwares to build superconducting qubits, as what they call. You might have had a lecture on that already. There are ways of having superconducting currents to behave like qubits, which are like atoms, ground and excited state energy level. Google and IBM are also working on it. There are trapped ions where you have atoms where you send out an electron and make it charged, then you can control them. There are a few companies which are looking at. You can use photons to behave like qubits, and there are different approaches for it, and I'll cover one of them tomorrow in more detail. There are ultra cold atoms, which is you can cool atoms to subatomic or millikelvin range, and then you can again control atoms at the individual atomic level, and you can do computation. So these are all like different hardwares which people have been exploring. So the colors of this indicates the temperature in which they work. There are these three which they can work in room temperature, but the others do need some low temperatures for them to work efficiently. Low temperature or vacuum also. Right? Trapped ions and cold atoms also needs high vacuum and then cut it. Superconducting needs low temperature to handle them. So there are simple postulates which defines most of the time. If you're from physics background, you would solve Schrodinger equations, you try to understand potential wells and all of those things. But if you're not interested at the elementary level of quantum mechanical problems, but if you want to see them as a resource, then there are these postulates of quantum mechanics which are serving as a resource, and understanding them very well will help us to look at quantum technologies. So we define quantum interference, superposition, and quantum entanglement, because these are something we see as resources which doesn't exist in a classical scenario. Right? If a cricket ball can't be in superposition at two places, but atom can be. Right? A single particle can't interfere. Waves can interfere, but in a quantum mechanics, atom can interfere, or photons can interfere with itself or with another photon, and they behave both like a wave and a particle, and there's entanglement. So that's another interesting phenomena which are serving as a resource for us to build a quantum technology. So these are some of the recent examples where people have built. Why, you might now recall when there was a claim of 53 qubits doing something better than anything any computers do. The numbers might relate to our earlier slides when we said if I have about 50 plus qubit, then it can cross the best of the supercomputers, and that's why the number above 50 looks interesting for anybody who are working on quantum computing. Because there are a lot of errors, they are not very clean, and if somebody has a very clean 53 or 55 qubit, then they can definitely solve problems which can't be done. But that's not the scenario right now, because there are a lot of limitations with what we have. But that's okay. That's how the problems have been addressed. This is another computer. It's a very specific purpose quantum computer. It doesn't solve all the problems. It solves one specific problem. It's called boson sampling problem. This was built in China years back. If you see, it just looks like we can see an analogy between the first classical computer, which was two-storied with all the vacuum tubes, right? These are all like optical components spread on a big optical table. There is photons which are sent. A lot of photons passes through various optical components, but the way the photons interact at the quantum mechanical level, it gives some results which no classical computers can do that. And people did find that this is a supremacy result. It means that it actually solved a problem which no classical computers could do. And this is also equivalent to calculating permanence of a matrix at a sub level. And that's another problem of its own interest. Maybe I will discuss them in probably another my tomorrow's lecture a little bit detailed. So there are broad classes of quantum processors which people have been building on, depending on various quantum hardwares, because here you need to look at which are the best suitable hardwares and what kind of problems it can do. And there's two broad classes which we call universal quantum computation and special task quantum computers. In fact, it's a very generic word which I'm trying to give. When I say special class, it means that it can only do some optimization problem, or it can do some annealing problem, or it can only solve a specific task, but it solves better than any classical computers do. And the other one's universal quantum computer, which means that just like our classical present quantum computers or classical computers, where we can define gate operations and you can write programs, and when we write programs we can change, the same processor can be used to solve various problems, and that's what is called universal quantum computers, and they're circuit based. Just like and or gates which we use in classical computers, there are some equivalent gates for quantum systems. I just listed them here, but we'll address them later on in our following lectures. This annealing problem is something which is very interesting here. If you see, there is a potential wells here. So if you want to find out which is the lowest energy level, so where is the depth? So this was our solution. This is what I want to get to. But there is very high chances of falsely identifying this is a ground state, because an object here will not know that after this there might be another down. So to avoid these false identities, false ground state identification, you can use quantum tunneling. So which means that quantum mechanics says that the particle and wave nature is a duality of every quantum particle. So there's a wave packet which spreads, and there's because of wave packet, there is some finite probability of tunneling from here to here. It doesn't have to hop here. There's a possibility of probability of tunneling from here to here, and that tunneling will help you to find out this as a solution with some finite probability, and that makes quantum annealing what we call a very interesting problem. How do we map it into a real life problem? You can treat it as there is various possibilities and there's only one ground state. And now the solution for your problem can be treated as this ground state, and various other places which you are going to get is not a solution for your problem. And now searching or finding a solution for the problem is equivalent to optimizing or finding ground state. So that's a special purpose computer, and these people have been using very efficiently today to solve routing problems, or even to look at traveling salesman kind of problems. Right? That's one of the simple one, but logistic optimization problems, finance related problems. So because this is a tunneling related one, and there's a D-Waves, one of the companies which initially started looking at it, and now various other people look at it. But the universal quantum computation involves circuits, which we are going to address later on. But this is just an example of operations you can do on them. Just like writing codes, you can write circuits to map your problem and find a solution. This is just another example of how we write programs on a quantum computer. If this is just probably a 5-qubit system. Because each one can be treated as 1 qubit. You do some operations, you do controlled operations. I can see each one as an atom. or a photon, depending on the state of atom in one, the other state can be changed. So because this is controlled operations, and you can just change this position state, right? If it's ground state or excited state or somewhere in between superposition. So we call them as one qubit gate operation. We call them as two qubit gate operation, and the combinations of them will be your programming language, right? You can write, this is almost like coding a problem. So you can define a problem. You can say, okay, this is my number of qubits I would need to handle that problem. And now I define sequence of operations, and whatever I'm going to measure is going to be my solutions. So we can see them in multiple ways. Every gate operation here corresponds to some matrix operation. This is what we call as quantum operations. So which means that they are changing the quantum state, which means that zero is becoming one, or one is becoming zero, or one is becoming a superposition of zero and one. All this possibility is going to happen with this setup here. So every time some operation is done, which means that some matrix is acting at that particular position. Right? So that's how the computer is built. There are also huge limitations today, which most of the researchers are working on. So quantum mechanics, quantum systems are fragile. I can't, hold atoms in my hand and move around anywhere around. I can't just get photons generated just from a torch battery. The way I need to generate photons are very complicated. The way you can stop atoms and then control the internet is very complicated. They may not remain quantum mechanical. The noise can affect them, which we call the coherence time. Coherence means the amount of time it will remain or it will retain its quantum properties is very, very small. So it means that you need to do computation at that fast time, right? Today, a microsecond is a very good time which some of the processors are working on, which means that all your operations has to be done before that, so that you get a result before it becomes classical, which means that it loses its quantum property. And now limited connectivity between qubits, because these are all like, when I talk about atoms or photons, you need to make them all connected to do operations very well. But the connections as today is still limited, which means that the number of operations, kind of operations you do, is still very limited. The quality of qubits also is very low. That's why even if people have got 53 or hundreds of qubits, they still can't solve many of the problems because the quality is low. There are a lot of errors associated with it. There are limited connectivities, and that the coherence time is also very less. So if these problems were addressed, the 50 qubits could have been very, very efficient. Now, this is not a negative news because when now it's the way technology evolves. When people build the first processors, even in the classical way, a lot of processors used to fail, and they were all very noisy. And one in a large sample was very successful. So that's why things were very, very expensive in the early days of discoveries. But over time, people learn to address each and every issue one by one, and they have mastered an efficient development. And the same thing is happening with the quantum hardware as well. But what we today address, most of us who work on the field, are there are near-term hardwares, which means that there are noise associated, there are limited coherence time, there is limited connectivity. With these limitations, what is that we can do? And come up with novel ways to develop algorithms which suits or which demands limited number of operations, gate operations, does some task. So that's something which we call as a near-term quantum hardware and NISQ era. That's what called it. But that's not that doesn't stop us from understanding nature and implementing some algorithm and proving in principle that this is going to work. And now if I have a larger number of qubits, I can efficiently. So there are some problems like, when we talk about relativistic quantum mechanics, relativistic dynamics, where things happen at very high speed or something is happening at black hole. And these are all like very inaccessible part of our universe. So if I want to simulate them, I have to simulate them using the laws which define them. So Dirac is one of the famous physicists who developed relativistic quantum mechanics model, and it today explains Dirac equations is what we call, explains a lot of quantum matters dynamics also. To simulate them, you can use quantum computers efficiently. This is one example of something on a very small number of qubits. You can simulate relativistic dynamics, which means that even without reaching a speed of light, you can see something built on a quantum computer with which mimics speed of light at a very tall, small with some parameter, right? You can fix a parameter and say now this is speed of light, and you can simulate on it. Now this classical computers can also do them today, but the algorithms to to use principles of quantum mechanics have been developed and have been tested. Various algorithms have been done over last few years. So the moment we are having a scalable qubits, larger number of qubits, you can actually implement them and understand various kind of features, right? So there is a okay. So that's again there's some issue. There's okay. I can. So there's a very simple video which talks about one of the first items that quantum computing was built. You can just see it for a moment. So you saw this in this video, and there is one of the earlier slides, which this is where I saw. There's a 5 qubit. This was an experiment which was done in ion trap system. You have a 5 qubit system, and if you need to do these sets of sequence of operations, you exactly do the way it is in this video, right? You chain lights, those items, and then you chain them in sequences. The moment you're chaining lights of some particular frequencies, the wavelength, their states change. Then when you make a measurement, you get your result, and that's something. So there has been quite a few experiments which people have done to understand nature at the subatomic level very efficiently, using very smaller number of qubits. This is okay until you get 50 qubits. The classical computers may not be of use, is what many of them might think about. But what physicists tries to look at is that okay, even if I have a smaller number of qubits, we can find some applications, or for example, we can try to mimic the nature very efficiently. This gives us two things. One, it tries to validate our theory, which means that okay, because I'm using a quantum state itself to define quantum mechanics, if they are exactly replicating what we see in nature, then our understanding of that phenomenon or process is correct. If you don't get the same answer, then it means that you can go and back and correct those theory. And people have been interested in using small scale quantum computers to understand various such kind of. This is one example where real time dynamics of lattice case theory is what we call what happens in vacuum when there are some interactions between subatomic particles. And there is a simple 4 qubit system which people have simulated. It's called a particle-antiparticle creation, which can be demonstrated using a simple 4 qubit ion trap quantum computer. Just like the previous example, which animation or like video which you saw, that's an ion trap system can do. And there is a problems like calculating ground state energy of helium and hydrogen plus molecules. Now, calculating ground state is always been a hard problem for quantum chemists, but just using a simple two-qubit system where photons pass through. When they are passing through, there is some way it takes different path, they interact, and you can always come up with an algorithm, which is a classical and quantum hybrid algorithm is what we call, but that does a very good simulation of or like calculates ground state energy very efficiently. So now people also have come up with an algorithm for a nitrogen fixation. You might remember that biologically nitrogen fixation is a very important problem, which actually helps in fertilizer industry or various other applications of them. So they have come up with a quantum algorithm where you can use classical computers to do various tasks which can be easily doable on classical computers, but there is a computing correlated energies which we call an interaction energy, right, of a big clusters, which is efficiently done in quantum mechanics, and after that you send it back to classical computers which can do and find a solution. So people have come up with an algorithm. Of course, even to do this you need a reasonably efficient quantum computers, and that can be solved if you have a reasonable number of qubit quantum computers. So even to understand some of these photosynthesis dynamics which I described earlier, so there are algorithms which have been developed to model the environment effect and what could be the possible dynamics under law you can get. What you need is a computer for which you can implement larger number of gate operations. So this way there has been quite a few development which has happened with which one can actually do a smaller number. What you need here is only small, right? 5-qubit system. And here you might need a larger number of qubit. And there has been quite a few cryptographic applications which people have been exploring, which mathematically studying about factoring problem, right? You want to have a public key or private key. You really have to. This is just an example. We'll address this again much more in our tomorrow's lecture. So if I have a larger number of or a smaller number of qubits, this is an example of a 4-qubit system where you can create a public and private key where it's nature which decides the secret security of your keys over a mathematical hardness. For example, today my OTPs are probably a public and private key, which we deal with banks, uh, involve mathematical hardness. But here I can use a quantum systems which create certain states, and because there is a postulate of quantum mechanics which does not allow information exchange easily is used here to generate public. And even a 4-qubit device has a very good application. In fact, one can actually demonstrate encryption, decryption using such keys, and this have been practically looked into. So there's a wide class of problems which has been uh, addressed, or people have been envisioning to use even the small scale quantum computers today, and we try to address some of them with examples in this lecture. So I think I was supposed to finish this bit more earlier, but I think it has taken more time. Let me try to go for my next talk without a break so that I can. So I think just to continue, I think it's in full screen, right? Ram, can anybody confirm?
Not at all, sir. It's all
Is
full
this full
screen.
screen now? Yeah, okay.
No,
No?
no, not it.
Okay, okay. I think it should be now.
Yes, professor.
Okay. So we'll try to, and the the earlier lectures, try to give a big picture of the problems that can be solved and some possibilities. So we'll try to quickly come to a mathematical framework of what defines quantum operations and how we are getting advantage with some example. So we can, I said, I use words like superposition, interference, and everything. Why it is coming is because in a mathematical framework, we see classical bits as a scalar quantity. We just have zero or one, but the quantum bits, which is defined by a subatomic particle level, what we call, are defined on a vector space, which means that it has direction associated with it. So, which means you can consider now as a sphere, and every point on a sphere has a unique configuration to define them. That unique configuration would say that a single qubit can be defined in various possible ways, right? Every point would give me different possible configuration, which in classical bit is only zero or one. Here, it's a huge lot of possibilities, and that's where superposition comes into a very big picture. And in the same slide, right side, I'm showing something else because that's a vector space. You can also have, so if you see every point on the sphere, I can associate them in a vector space. I can also get some phase associated with it, right? An angle associated with it. And now the phases would end up giving us a positive and negative sign. And now that allows, because of here you can see there's a just like a water waves, water is going through. If you are making a slit for it to pass through, then there is constrictive interference and destructive interference, and that's possible. And now, because you can have a single qubit going in superposition, you can have them interfere and have some controlled interference. So just like this, yeah, right? There's some different intensities, but you can see at some points it's brighter than the other one. So it means that there has been constrictive interference at that point, and there's been destructive interference at the point where you have lighter product. So you can control them, right? You can engineer them. Now that's how superposition interference comes into a picture, which we can define them in a very mathematical sense. So the way we, in a quantum computation language, we use Dirac representation to describe qubits very efficiently. Classical bits are just zeros and ones, but here we use matrices because they have a vector space. To make it even much more simpler, we write them as in a Dirac notation, as a Bryant-Ket notations is what we use. So zero, which is a quantum bit zero, is represented by 1 0 submatrix, and one is represented by 0 1. Those are conventions. Now, if I want to think of physical device to be built, I can take photons with horizontal vertical polarization or a spin with up and down. They can represent 0 or 1. Now, because I can have any point on the sphere, I can define it by alpha and beta or any trigonometric component like this, and every point would have a unique space. So that's something which is our basic element for quantum computers, which is called a qubit, what we a logical qubit or a computational state. So in an atomic system, the way we try to realize them, it could be like an atom, an electron, which is here, it's treated as zero. If it's on the outer orbit, it's treated as one. But if there's continuously driving between these two, you can end up having a superposition state. Right? So it's the composite system, which means that if I have two or more, I think I had written down the notation earlier, but now the way matrix does in a matrix dimension, we call them as Hilbert spaces. I can combine, if I have two particles or two atoms or two qubits, this will write them as a tensor product. It's not addition, right? In classical system, we write them all as an addition, but in a quantum mechanical system, because they have superposition possibilities, it become tensor products. So it means the dimension increases. So the way you multiply is that 1 0 and 1 0, 0 0 becomes 1 0 0 0, and 0 1 tensor product, which means that I am taking one of the matrix, multiplying with the other one, which is 1 0 1 0 0 1, which means that this becomes 0 1 0 0. So now this is the four possibilities of a 2-qubit system. So now if I have to mathematically write down for like 10 qubits or 20 qubits, my matrix dimensions becomes very large. That's still a better way and natural way of looking at it. So there's another interesting phenomena which I described earlier. It's called entanglement, which itself was a very uh, debated, argued phenomena, which Einstein could not believe that something like this can actually happen in nature if called as some spooky action, or he called it as a paradox. So what it says is that you can actually take two particles. So now it's easily understandable from this Dirac notation. Right? I can take two particles and I have some kind of superposition possibility, which means that 0, 0, 0. Now, if I have this possibility, whenever I make a measurement, it either gets into this state or this state. So it means that even if A and B are spatially separated to be, it can be hundreds of kilometers. The moment I get to know what is the state of my A, instantaneously I know what is the state of B. So it means that there's an instantaneous information exchange, which was something was not easily acceptable, because what people thought, or what Einstein also believed, that you need speed of light to have any information exchange. So if information has to go from A to B, the minimum time needed is the time taken by the light to go from point A to B. But here, instantaneously, when you measure, you are getting an information. So now this is for something which we call as, this is not violation of relativity. In fact, people have looked at it in various ways, and there's a good explanation for that. There is an instantaneous information exchange between A and B, and that's called as entanglement today. It's very well understood, and people have demonstrated experimentally and communicated thousands of kilometers. Uh, so what these three principles in summary would do is that superposition allows, if I have to look at it as a computational resource, that explores all possible options or solutions for my problem. Because superposition can explore everything simultaneously, interference allows us to engineer constructive interference towards a desired result. Because the whole computation's task is to find a solution for your problem. And a destructive interference are undesired options. A constructive interference will be a desired option, and destructive interference will be an undesired option. If I can engineer my interference, which means that I'm engineering a solution. Entanglement allows instantaneous and secured information exchange. So that's secured, that also helps in securing quantum information to going from one to the. So now these three resources, now I can see how, if I have 8 qubit or a 3 qubit, sorry, if I have 3 qubit, I will end up having 8-dimensional invert space, because it's 3 tensor. So it's a state, a superposition of all these possibilities. So superposition means that's something which I can't write a classical state here. What happens is that whenever I make a measurement, it just collapses to one of those possible 8 options. So with a probability of 1/8. So this is an amplitude is what we call, it's a probability of 1/8. So if I have n dimensions, then I can write them with such kind of possibilities, like n possibility of a solution. So that's how we build a large, mathematically construct a larger number of qubits in a system. So if I have 2 to the power of n dimension allows, 2 to the power of n dimension system can be constructed with n qubit. In general, a qubit can register number 0 to 2 to the power of n simultaneously. So now that's what becomes very, very interesting. Sounds too good to be true, but it is, right? So because I can have superposition, if I just have n, then, if I just want to store some number between 2 to the power of, then I just need n qubits, and measurement collapses to one of them. So now to do computation, then I need to do some operations. That is called as a linear transformation, and that should preserve vector norms. What do you mean by vector norms mathematically? There's some words, but simply, if there is an atom or if there is a photon, it has to be there somewhere, whatever state it is. So a probability of it has to be 1, or sum of possible probabilities of possible configurations has to be 1. So that has to be preserved. So that's what we call preserving vector norm, right? And now in a 2-dimension linear transform that preserves unit circle. A unit circle would also mean I have to change, if for example, I'm changing a polarization of photon from H to B, it has to change in some particular, I can't say that, some photons are lost and some are remain, it's a single photon, right? So there's a linear transformation of that state, and that's This is an example. Yeah? We call a first simple thing is bit flip. This is a computational operation, but in a physical terms, you can say a spin of an electron is going from up to down or down to up. This is one. This is one of the operations. How do I define computationally or mathematically? Now I said there is matrices which we define gate operations, but before we go for gate operations, we can see this simply here, right? A bit flip, a bit flip, which will do changes 0 to 1. So it means that matrix 1 0 becomes 0 1. So I need a operation which is of this form will do. Now the same operation will change something sigma x on 1. Sorry, this should have been 0 1. It is written 1 0. That changes it to the state. So now you can keep doing bit flip operations. You can do some Adamant operations, which means that I have to also exploit superposition. And now 0 should become some superposition and 1 has to become something else because they can't be the same, right? If I'm giving the same, it doesn't help. So the sign will come into the picture to distinguish between 0 and 1 when there is some operations. We call them as Adamant operation, which creates a superposition of two possibilities. So there's a matrix which preserves norm. And if it does an operation on 1 0, I end up getting a superposition of this form. If it acts on 1, it ends up doing operation on this form. So this simple question would be, what will I happen if I do this operation, Adamant operation twice? We can say that if I'm doing it twice, you get back the same state which you want to begin with. So now these define universal set of operations. So which means that any qubit, if I can control the state, then I should be able to do control operations. There is an operation between them. So if I take qubits and if I can somehow find out some physical way to do this set of operations, and this is a two qubit operations, which means that depending on one, changing the state of another. So for example, a C0 gate, this operation on a two qubit system, if the first qubit is 0, nothing happens to the second. If my first qubit is 1, the second one flips. So if you see here, nothing happens in the first two, the second two, there is a change of the second qubit. We call it control not bit. So if I can implement this set of operations, then I can actually do any complicated quantum computers. That's current definition. Okay, I say universal set of gate operations. I can define complicated problems, convert them into gate operations, and then implement them. The difficult task is implementing them. I can do. But now, other important thing comes is measurement, right? So when what we are telling about quantum states, that in superposition, I can't simultaneously, they will be in superposition, but when I make a measurement, I will either measure this or this with a probability of 1 by 2. And this is our quantum mechanics measurement postulates. Measurement changes the state, which means that it becomes either this or this. It won't give you both the answers simultaneously. Repeated measurements or repeating measurement gives same outcome, right? So if my geometrical way of looking at it is like this. If I have a superposition, I make a measurement with 50% probability, I'll get 0. With 50% probability, I will get 1. But if I repeat them continuously, I can end up telling what could be the possibility of the coefficients of that quantum states. So you can have not just 0 and 1, you can take any orthogonal states and I can still implement such kind of gate operation. You can also do partial measurements. When you say partial measurements, it's one simple example. I take a two qubit system. I will have 0 0, 0 1, 1 0, 1 1. Other 4 possibilities, but I'm not having 1 possibilities because I've engineered my state like this. But we are also telling that the quantum state should preserve norms, which means that the sum of this probability amplitude, square of that probability amplitude should be 1. So it means that this becomes 1 by 4, 1 by 4, and this becomes 1 by 2. So the sum will become 1, so which means that these are only 3 possibility states. Now let's say I'm not making a measurement on both the qubits, I'm going to make a measurement on a single qubit. So this is first scenario. The first qubit collapses to state 0. And which means that I'm losing this possibility. I don't get this because first qubit becomes state 0. So my output will be and 0, 1. I will get these two as an output. But if my measurement collapses first qubit to state 1, my output will be only this, and this comes with 50% probability. So I can make a partial measurement on a first qubit. Similarly, I can actually make a partial measurement on the second qubit. If my first qubit, no, my second qubit becomes 0, then my output state would be 0, 0 and 1, 0. So that's the superposition. And if it becomes 1, then I will only get this output. So this can be done even if I have a very large number of qubits. So that's how we try to do some computational operations, and you make partial measurement on some qubits, you get some information, and you continue doing your operation. So these are all like possibilities. So the way we differentiate classical and qubits, classical bits and the quantum bits, that in classical bit you can measure them completely. States don't change by measurement. Whatever is there, it exists. You can copy a classical bit, and you can also erase them. But quantum bits are can be measured partially. You can't measure them completely. Like I showed, the partial measurement can be done. You can alter the states, and states also gets altered by measurement. When you say altered, which means that you can't capture the superposition when you make a measurement. You either get it. But other important thing is that no quantum states can be cloned. You can't actually clone a quantum state, or you can't even erase them. So that's something which there is no cloning theorem and no erasure theorem in quantum mechanics. That's one thing. So this is another very famous or a very simple and profound way of looking at the uniqueness of quantum states, what we call the qubits. So no cloning of any arbitrage, which means you can't copy state. So let's example. This is just a simple example. Right? What do you mean by no copying of a quantum state? If I my whatever photocopy machine does that, you have some information, everything is copied to another one identically, which means at the bit level, if it is a classical bit or if it's a bit 0, can I make two copies of 0? If it is 1, can I make two copies of 1? So what it says is that a linear transformation. So which means that I need to have an operation which preserves norm. We were defining this gate operations, right? So a linear transformation is what we call them. If I had defined a linear transformation, my state 0 plus 1 will end up becoming 0, 0 plus 1, 1, but it does not become two copies of the same. So which means that the information, which is 1 by square root of 0 plus 1, is not copied here. You have got some other two qubit state, right? So which means that 0 becomes 0, 0, 1 becomes 1, 1, but a superposition of these two, 0 becomes 0, 0, and 1 becomes 1, 1. It doesn't become 0 plus 1, tensor 0 plus 1. So which means that you can't copy a quantum state equation. So this is not the same as two copies of the same thing, and this is a simple way of defining no cloning theorem. One can actually have a slightly more difficult mathematical proof for it, but this is something which is going on. So now most of the computation on quantum states are defined using linear algebra, because quantum states preserving the norms and having complex conjugates, everything maps up very well. So I can define a complex conjugate of any complex number, because I said amplitudes, right? When you say superposition of amplitudes, the amplitudes can have phases, it can have negative sign, it can have complex numbers associated with it. So the way we define, so there's a vector, we call it a sket, and there is one more, this is sket and this is bra. The two things we can define. So sorry, I think this is again a sign error here. This should have been the same thing. So the vector, which we call as bra, this is a complex conjugate of this values. So when we take an inner product of these two, then we end up getting some value, which is again a measurement output, is what we call probability values. So it's just two matrices, right? I have a matrix here and I have a matrix here, but the moment you are changing the way the arrows are written, which means that the column vector is becoming, sorry, column matrix is becoming a row matrix with every element having its complex conjugate. If I multiply, I end up getting this value. So, which means that a vector quantity is getting reduced to a scalar quantity, a single value. So, this we call a measurable one, probability value, which you are going to get. A tensor product is another example which we had already defined how we can write multi-qubit states. So a linear algebra helps us to do a lot of operations on a quantum computer, right? So for example, if I have any complex conjugate A, I define A star like this, A transpose, which are defined this way, and Hermitian matrices, because there is a Hermitian conjugate exists. Um, any measurable quantity in quantum systems are real values because we measure. So the Hermitian matrices plays a very important role because they do have such kind of properties when you make a measurement, right? So there's subject. So we calculate norms which are directly related to a probability values of that particular inner products of all of them. So this a simple matrix which is defined from the linear algebra are very fundamental to define operations on a quantum computers. So let's quickly review whatever we discussed about the quantum states, superpositions, interference, and all in terms of postulates, including the measurement. There is people mix words many times: quantum mechanics, quantum physics, quantum computing, and everything. How do we define them? Very simple. So quantum mechanics is a mathematical language because it's not just a mathematics with certain boundary conditions. So that's what we call as quantum mechanics. It's much like calculus, but with some boundary conditions. Classical physics, just like the way classical physics uses calculus to explain, quantum physics uses quantum mechanics to explain nature. And in a similar way, a quantum computers can be thought of Boolean algebra and classical computers can be thought of as Boolean algebra, and quantum computers are reasoned about with quantum mechanics. So they are more postulates. I just described, I initially told what are the three takeaway resources. It is superposition, interference, and the entanglement. That's a resource, but those resources are controlled by the postulates. So now postulates are simple. When we talk about defining a qubit, what does this mean? It actually says when I define a qubit, I also define superposition along with it, and I call them as qubit. And how qubits transform, which means that evolving. You need to do operations. You need to change states of them, and that's it. You make a measurement, it collapses. How qubits combine together into a system of qubits. Right now, this is just what we have defined. Say qubit superposition is postulate one. Right now, postulate two is evolution. So we defined NOT gate. We defined matrix operations earlier. So now it gives some outputs. From input becomes some outputs, and they are all defined by set of operations. So if I am doing this matrix operations, I'm changing the state of my system, which means that I'm evolving my qubits. So which means that I'm actually doing a computation task. Changing the state itself is the simplest of the computation tasks. A sequence of such kind of states can become a complicated computational task. Right? There is again, this comes from a standard quantum computing textbook, Nelson and Chance. An evolution of closed system is described by unitary transformations. Thus, matrices define unitary transformation that the state at some time, time t1, is related to state at two. There should be some operations which takes from one time to another time. So that's what we call as linear transformation. So if I say some state psi, if I do some unitary operation, I will get psi prime, which means that my output. So this is my input, this is my output, this is some transformation. And these are some examples of different kinds of transformations. But now if you see all these unitary operators, what we call these operators satisfy unitary condition. You can look at what unitary conditions would be. So you have to take a complex conjugate and transpose of that, multiply them, and you'll end up getting a diagonal or unit matrix. So which means that there's a probability conservation associated with this. Is the example of it, right? You have U, You take U dagger of U, it will be the same because there's no complex number associated with it. But even if you have it, you will end up having an identity matrix. There's two to cancel. So any matrix U, which along with U dagger U becomes one, they will be defined as unitary matrix. And this can be defined as a implementable operations on any quantum states. So if anybody thinks that this is an operation, can it be done on a quantum computer? If it is unitary, yes, you can always find some way to implement on a quantum computer. Right? Now the measurement. I did give an example earlier where you have a 2-qubit system, you can make measurement or partial measurement, but you can give a very generic definition that is described as a collection, described by a collection of measurement operators, which means there's possibility of many operations, but it gives one output. So these are operations acting on state space of system being measured. When index M refers to a measurement outcome that may occur in an experiment. So if the state of a quantum system is I immediately before the measurement, then the probability that measurement M occurs is given by this. So if I know the state, if I know what kind of measurement I am doing, I can expect the probability of my output. That are defined by a completeness equation, and we can look at that more. So a simple again. That's a very generic form, but this is an example, right? I was telling I can define a measurement operator like this, right? So which means I am going to measure a state in, a state in state zero, a quantum state in state zero. M1 is I want to measure a quantum state in state one. So what this would say is that it will calculate me the probability of finding the state in position or in a qubit state one. M0 will give me a probability of finding the qubit state one. So in a matrix form, it is like this, right? So M0 is written here, M1 is written. So you see here, M011, M0 and M0 dagger, that becomes M0. And then you will end up getting the probability of modulus A square. That will be the probability of finding in state zero measurement output. So if I was using M1 and M1 dagger, I would have ended up getting P here and not A. So if what it says is that I can choose whether I want to measure in M0 or in M1, which means that state 0 or 1. I can use this matrix and make a projective measurement on them. That's what we call, we project them into that particular state and then say, okay, with this probability, I can measure the state with so-and-so value. So even when I have multiple qubit, I can do similar kind of measurement. So there are a lot of positive configurations, psi1, psi2 in tensor product, but on each one of them, I can make a set of measurements, right? Psi1 and psi2, you can write a tensor product, then you can make measurement on those particular state. Say multi-qubit state, as we said, a quantum computer can be defined as a device where you can have n qubits in multiple possible superposition states. So this is a 0 and 1 to the power of n, which means that my x is in tensor product of larger number of qubits, and I can get a norm should be preserved. A superposition is also defined with the norm value here, which would say the modulus of the square would be the sum of probabilities. So what? So there are class of gates which people have defined, but we would still see the first sigma x, sigma y, sigma z, which we also call as poly gates, and an Hadamard gate, phase gate, and control node gate. So if I can do them, then all this also becomes part of implementable gates. So this would help me or help us to do operations on quantum computers very efficiently, right? So a quick run into converting them into circuits, which kind of defines how we do computation. So there is a way, all those metrics which we define, but we can write them all in terms of notations also, right? So a qubit is always defined by a line going from left to right in quantum circuit. If I want to write a quantum circuit for it, so if I have to define an operation, it can be H or it can be X, which is poly X, poly any operations you want. If my input state is psi and the output state would be H plus psi because this is H, right? So if my input state is psi, output state would be, you can take an example here, right? I give some input which is superposition, 0 plus I1. Hadamard operation will end up reversing this into one of the basis states because Hadamard will do that. It's a simple matrix you can actually write down and you can look at it. This will be 1 by root 2, 1 by root 2, a column vector, and this will be a square matrix of 1, 1, 1 minus 1 divided by 1 by root 2. So if I do that multiplication, I will end up getting an output state to be 1. So this is a simple single qubit gate operation description. And measurements are indicated by a circle on a qubit system. So this would say that this qubit is measured, and after this, the moment you get a double line, which means that it's a classical information. This is a quantum information, which means it can actually be in superposition. But from here after, it will not be in superposition. That's a classical. The two qubit gate operation are defined like this. I can take two qubits. It's a control not operation. So what it says here is A and B, but this is a control. This dot would say there's a control. This is a not. Depending on the state of A, B changes it. So it means that if A is 0, nothing happens to that. If A is 1, B flips. It's just simple and this here, right? So addition modulo is there. If this is 0, if this is 1 also, it remains 1. If this is 0 also, it remains 0. But if this is 1, then if B is 1, it becomes 0. Right? If that is 0, then it again remains 1. So it's kind of, if B is 0, it gets flipped. So depending on the state of what your control bit is, you can get a control. Similarly, one can define control not gate operations. Mathematically, one can write them all this as tensor products, write a big, this will be 3, right? 8 cross 8 matrix. You will end up getting some output, but you can also define them with the circuit like this, a simple 3 qubit circuit. So what it says is if state A and state B, only if both of them are having 1, the third one flips, otherwise they don't flip. Right? So that's the definition. So similarly, you can always do a sequence of operations like this. So I can take psi1, I can do Hadamard on both of them. I will get an output, and again I do a control not gate. I can do Hadamard, and I can think of now. This is just a simple example showing you a circuit and then how our mathematical operations looks like. So I have two qubit. I am taking psi1. Psi1 is 0, 0. Both of them will start with 0, 0, right? We don't change anything. And the moment you do Hadamard operation, both, it means that 0 is becoming 0 plus 1. Again, this 0 is also become 0 plus 1. So after I do H, I will end up getting psi2. So now psi2 is this 1 by root 2, 0, 0, 0, 1, 1, 0, 1. So the state here is this. If I am again doing a control not, which means that control on the first node. Now we can see here in this state 0, 0, nothing happens. First qubit is 0, second qubit, nothing happens. My first qubit is 1, second qubit becomes 1. And if my first qubit is 1, second qubit becomes, if it is 1, it becomes 0. So what is happening here is this is becoming 1, 1, it's as shown here, and this is becoming 1, 0 as shown here. But overall, if you see the psi4, because at the end you can rewrite this expression, again it looks like the same thing. And if you do Hadamard operation, you end up getting back the same state. You begin with state 0, 0, your output is state 0, 0. But if I begin with state 0, 1, the same circuit will give me different output. So it's just do this multiplication, you can see. If my input is 1, 0, I end up getting 1, 0, same thing. I don't get anything So similarly, if my input is 1, 1, I end up getting 0, 1. So depending on my input, my output result changes. And there is this operation which is fixed here, and you are going to. That's just an example, right? So, but what is interesting here, right? So the way you look at, sorry, if you look at this operation, you see if my first qubit is 0, right? So you don't, there's nothing which is happening, but you see it slightly differently. Let me look at the second qubit. If my second qubit is 0, right, there's nothing which is happening. If my second qubit is 0, there's nothing that is happening. Both input and output are the same. So if you see the top two, when my second qubit is 0, nothing is happening to the first qubit. They just remain what it is. If my second qubit is 1, my first qubit is flipping in the output. Second qubit is 1, my first qubit is flipping. So this techniques, what it is telling us is there is 1, 2, 3, 4 single qubit operation and 1, 2 qubit operation. But I can replace this effectively with a simple reverse control knot operation. So this is one of the simplest and the most profound way of what we call circuit optimization problems. Right? This is very simple, but this is done in a very large scale. Where sometimes we develop an algorithm and we define a circuit, and it means that it needs a lot of gate operations. We want to minimize them, so we identify there a combination of gate operations which can be replaced with one simple operation, which becomes easier for an hardware to implement. And this is one such simple example where a 4 single qubit and 1 2 qubit gate operation is replaced by a single 2 qubit gate operation just by reversing the controlled bit to action. Control bit position is changed in this. Like this, there are various circuits optimization which people can look into. But there's one, I think there's a couple of simple examples of the qubits playing a role in computation, and computational advantages can be seen even at a very, very small scale. One does not have to see advantages in very, very big number of qubit system. But the superdense coding is very, very simple and important problem. And it can be explained in a very profound simple. Alice and Bob are in two different parts of the world, right? So we can always split them. Now Alice has 2 bits. It can be A and B. It's just 0 or 1, 1, 0, any combination. She would like to communicate these 2 bits to Bob by sending him a single quantum bit. Can it be possible? So that's the first question, right? Because in a traditional way, if I have to exchange 2 classical bit, I need to send 2 classical bit from A to B. Is there some way where, because quantum mechanics allows superposition, can I just send a single qubit and then exchange 2 bits of classical information? It looks strange, and Bob must just have 1 bit of information about the pair. And this can be accomplished using quantum states, which we call as entanglement. And this is something which is not possible with the classical sources at all. So what it says is that just by sending 1 qubit, I can actually exchange 2 bits, or I can actually communicate 2 bits to Bob if Alice and Bob had already exchanged an entangled qubit state. So now that's something which, you have entanglement as a resource. The moment you have, then you just start to send 1 quantum bit to exchange 2 bit of information. So the way we look at this is a simple entanglement bit definition, which means that I take resource 2 qubits in those particular configuration. And they are at 2 different parts of the world. Like this, there is a state, Alice is here and Bob is here. We don't know which of the state is. If Alice is 0, Bob is also 0. If Alice is 1, Bob is also 1. But we don't know which one because they are in superposition. So what superdense coding would say that if A is equal to 1, Alice applies a unitary transformation to qubit A. Because Alice anyway knows what has to be sent, right? If A is 0, she does not do anything, right? That's the first step. If B is equal to 1, Alice applies the unitary transformation to a qubit A, because Alice can only do operations on the qubit she has, and Bob can only do operation on the qubit he has, right? So there is nothing, they can't do operation on the qubit which is with the other person. But all that they have is both of them initially shared entangled state. So that's all. Alice sends qubit A to B. So it means that if Alice has to communicate to 1, Alice applies unitary transformation to qubit A. If it is 0, she doesn't do anything. If B is 1, Alice applies unitary transformation 0 to qubit A, and if B is equal to 0. So it means that A and B, both values are there. Depending on what is A and B, Alice does the operation. After that, Alice sends qubit A to Bob. That's all. Because there's only one qubit with Alice. But Alice wants to send A and B two information on it. So she just does that sequence of operations, right? Now, in the circuit language, I was telling you, right? Now this is a quantum bit. These are two classical informations I need to send. If Alice is A is 1, and then it does a transformation, which means that a qubit will get a minus phase because sigma x does the multiplication to a qubit. And if B is 0, right, then it does nothing. But if B is equal to 1, you do a control not operation. It's a flip. You just flip the qubit state. So now there's two operations has been done on a quantum bit depending on what is the value of A and B at a time. After that, Alice just sends this qubit. She doesn't even have to measure. She just sends it to Bob. Bob, on his end, right, applies a control not gate and an Adamant operation. That's all. Because what now, Bob had only one qubit before, but Alice sends one qubit from his side to Bob. Now Bob has two qubits. From two qubits, he just does two operations, and output would be A and B. So there is two classical bits, but now we end up having a quantum bit which is carrying an information of A and B straight away. Now this is a very simple, but you can see that how easily two classical bits can be communicated just by sending one quantum bit from Alice to Bob's side. All that was needed was two controlled operations on Alice, depending on what was the classical state on the Alice qubit, and communication of Alice qubit to Bob's qubit, and 2 bits of information. This has actually been scaled up to larger number of qubits. So what is the minimum number of quantum entangled state needed to communicate a larger number of classical information from A to B? So there's a extended versions of super dense coding, and people have shown that this is possible with a larger scale, right? So this is I just gave one example, but we can actually see for any given 00011011, Alice will end up, Bob will end up getting the state, quantum state, but there's a phase, that's all. But output will not calculate phase. It's always a probability, right? So in spite of possibility of superposition, these operations ensures that with 100% probability, the classical bit is transferred to a quantum state, and the measurement will give you the output you are going to get. So that's something which is one of the useful and important proof of advantage of quantum states. This entanglement is playing their role, the superposition is playing a simple quantum gate operation which we had decided to also helping. Similarly, there is another interesting demonstration one can actually do with qubits is teleportation. So teleportation has always been a fascinating topic for people. Like, can one teleport an object from A to B? And these are like big problems which nobody knows whether it can be done. They have some complexity. But what quantum mechanics can say is that a quantum state can be teleported with certain accuracy by using some quantum resource. For example, I can, similar to super dense coding, where I can take entanglement between two particles, two entangled state, and I can, just like in super dense coding, I have two classical bit information. Here I take a quantum bit and I want to teleport. Teleport means you are destroying the state psi here, and then you're recreating this psi at other place. So you're not sending psi across a channel. If you see the schematic, you can see here there is a separation between Alice and Bob, but there is no transfer of any quantum state from Alice to Bob's side. It's only a classical information which goes through. So which means you can very securely teleport a quantum state by using certain protocol. And what this needs is a simple control not gate Hadamard operation on one of the entanglement bit which Alice has and an unknown quantum state which has to be teleported. And you get a measurement output you share depending on the control gate operations you can get, right? So I think I'll, in the interest of time, I'll not describe the details of the mathematical steps here, but one can work out from the circuit and you can teleport from state A to B, right? So there are advantages of using quantum states because of this interference which comes. People can always get confused with the probabilistic behavior and the quantum state because they think, okay, whatever quantum states you are going to measure, they are anyway is a probability output. So what is the difference? But there is a huge difference. But, when you are trying to, here I can say a probability of four possibilities are defined by P001 and this possibility is also different. But every time if you are making a measurement on a quantum state, then you are getting a probability value and both of them are equivalent. So there is no difference. A quantum algorithm, if you are making measurements, they are the same because you are not exploiting the interference phenomena here. But the moment you are bringing in interference phenomena, which means that a classical probability will always have a finite value which you are going to get without any phase associated with it. But when you're trying to have an amplitudes, so there are places where, from zero, I'm going to get some particular position here. From one, I'm going to zero. From two, I'm going to zero, which means there is amplitudes which are coming from different places. One can have a positive sign, one can have a negative sign. You can have a constructive and destructive interference. And the measurement on that will give you a very different probability value compared to what you can get from here, right? So that's where amplitude comes into the picture. And there's this simple example here, no interference versus interference here, right? So if I take state zero, do an Hadamard operation, make a measurement. Again, you do a Hadamard operation, you make a measurement. You will end up getting simply what you see here, psi1 will be 0 and 1 with probability because Hadamard takes it to superposition. Because it is collapsed to 0 or 1, you again apply an Hadamard, you end up getting 0 or 1 or 0 or 1. You will end up having probability of finding this state or this state with half the probability, right? But if you are not making a measurement, if I'm doing an Hadamard operation and again an Hadamard operation, I end up getting state 0, what you begin with this one. So the measurement makes a big difference. If you're making a measurement in between, you're not getting any quantum advantage. But if you're not making measurement, interference is playing a role and you're getting a quantum advantage. So I think there's a simple example which we always think about is a phased kickback register, which means that I have to exchange information from one qubit to another one, because these are all like part of computational tasks. If you try to build quantum computers, these operations becomes very, very important, which means that if I take two qubits, one is in superposition, other is one. What I mean by phase kickback is a phase from here, first qubit has to be transferred to, second qubit has to be transferred to first qubit. What that will do is that I will be able to use that phase information, make a measurement on first qubit and know what was the state of the second qubit without making a measurement on that, right? Now that's where we call phase kickback on a control register. Depending on the phase, I can actually, without making a measurement on second qubit, I can decide what operations I have to do because I need to do a controlled operation to do computation. So there's this simple example where I have two qubits. One is in superposition, other one. Now what it is saying is that if I have 1, 0, and if I'm doing a control NOT gate operation, if my minus sign is there in the first, I get it transferred. So it means that my first qubit would also have phase transferred associated with it. So if my both of them are, see here in all these examples you're seeing, the phase of the first qubit after you're doing control node operation is carried to, sorry, the phase on the second qubit is carried to the first one. Here also, this is a phase on the second qubit, it's carried to the first qubit. So here also it gets carried to first qubit. So if there is a 0 or 1, depending on what you're going to get, you will be able to get a phase. So this is one of the simplest form of phase kickback algorithm, a simplest version, but this are built up into a more complicated phase estimation algorithms, and not just kicking back and you need to estimate the phase of something without making a measurement, right? So I think with this, I will have exceeded my time and I will end talk. So thank you very much for to you all for
Yeah,
patience.
thanks, Professor. So it's been a little bit overshoot. So there are
Yeah.
about 30 questions. Will you be able to take?
Yeah, okay, I can take. So let's see what's the. I can
Please
take
see
a-
how much can you take. Yeah.
Yeah. So I have to go to.
Q&A at the bottom.
There are comments. There are. Okay. There is. Okay, I got them now. Okay. Sir, is there any scope for computer engineering student to in the field that how time to get into it? So in fact, as the whole of my talk was trying to keep the physical content very, very minimal, right? Anybody can work in the field, but you need to pick the right tools. If you're coming from a mathematical background or a computer science background, the best tool for you is a linear algebra, and then try to understand the quantum dynamics from linear algebra perspective. A matrix is common for everybody. You need to know a good amount of matrix operations, and linear algebra is going to help you. What you need to know is the normalizations and the set of unitary operators and how you are going to look at them. And the rest, the physics, you don't have to deal with it, right? So from physics background, we try to understand it from Schrödinger's point of view, try to solve with various physical constraints. But all those things are not needed if you are coming from a computer science or mathematics background. So I don't think there is any difficulty for you to look at it, but you need to approach it with the right tool from your domain. I would say linear algebra is the route to get into quantum computing. With that, you need to understand the Dirac formalism and the matrix representation of it. You can look at it. So what can be an example of algorithm in BQT, but not in NP? Okay. So there has been quite okay. So it's not in NP or P. Okay. So I think this is slightly a difficult problem to be answered at this problem this state. But there has been. I would suggest you to look into a complexity zoo. Or what we call an algorithmic complexity zoo, one of the web pages maintained by Scott Anson. So he has maintained tens of, I think hundreds of algorithms and then defined them under these categories, right? Which are NP-hard, complex, and which are solvable, which comes under BQP classes. And these are like mathematically defined problems one can look into. And I think I would suggest you to look into that web page. Or it's actually a blog which is maintained. If you just look at complexities, algorithmic complexity zoo, and you'll get to that. So there are number of atoms representing one portion of information. In case of teleportation, are these number of atoms? Yes. So when we talk about teleportation, we are teleporting a particular information. So if I have to have I would need two atoms to teleport an information, two atoms in entangled state to teleport information of one qubit system. So it means that every teleportation is a teleportation of a quantum state. So if I have to teleport some objects, what means that I can't do it by in principle directly, but I can convert them all into information and teleport an information. And from that information, I can reconstruct. I don't know if that is what the question is meant to, but that's what I can understand. Okay. Ask what is the difference between logical and physical qubit? Okay, this is a bit of different. When I was trying to tell you that there are errors with the qubits because of the hardware's limitations, and sometimes I want to change it from 0 to 1. It might not become 0 to 1 because of the way I do operations. They are not very efficient. So these physical qubits are the qubits which we are using directly from the physical entities, which are our bread or butter, whatever what we call as elements, basic elements. Let me put it. Photons, electrons, superconducting qubits. Are, when we talk about logical qubits, which means that you are encoding multiple physical qubits as a single logical qubit, such that you can represent some state with the combination with a multiple qubits, so that operations on one may fail, but the majority information is carried forward. So that's where logical qubits come into the picture. So people are working towards building logical qubits, which can observe errors. So it means that I need to have thousands of physical qubits to have some tens of logical qubits. Correctly. That's how we try to define them. So logical qubits is not a real physical entity, but it's a representation of a computationally relevant qubit state. Okay. So third year student, currently I have minor in quantum mechanics under QM. Can you please guide us how students so yeah, I have to take courses to learn work problems. So there are standard quantum tech information computing textbooks, Nelson and John, Neil Laflamme's notes. There are multiple lectures available online, and courses have been offered. So the most important is you need to get into the rigor, solve problems. That's the only way you can understand and appreciate things in more detail. So, which problem is best suited? Is there any studied guideline on which problems are best suited for different architecture? Like, okay, so there has been problems. Okay, architectures would mean that the connectivities of qubits. So people try to look at the connectivity, like ion trap have all-in-all connectivity. So the number of gates required for them would be different. So it's not about class of problems here, because if you're talking about universal quantum computation, you're trying to see what algorithms needs or have a connectivity issue. So which one, for example, if some algorithm needs a huge gate operations between 1 and 8 qubit, but 1 and 8 qubit are not physically connected in a specific architecture of superconducting hardware, then you can't efficiently implement on it. But somebody might have built another superconducting architecture with 1 and 8 qubits are connected, but the others are not connected efficiently. So the geometry of superconducting qubit itself will be very different. So that's what people are trying to work on. Everybody are trying to come up with different connectivity architecture so that you can figure out which geometry has a more efficient connection. So even within the superconducting qubits, one architecture might efficiently implement one algorithm, and another architecture might implement some other algorithm more efficiently, because the number of gates needed would be very less for that architecture. So you can't actually say which one can do efficiently. But the way currently it has been divided is an optimization problems can be efficiently done with annealing problems, and the gate-based can be done with Arduino. So coherence time is bit better with ion traps, Connectivity is better with ion traps, but there are other issues with ion traps compared to superconducting qubits. The superconducting qubits have noises, microwave noises, which comes into them, and these are the factors which matters these days. Current in the current scenario, more than what problems are most suited for ion traps. What is an algorithm to do error correction in? Okay, there are various error correction algorithms, which is called steam codes. There are 3-qubit error codes. There are various algorithms which has been developed, and you can that itself is a separate course one can take. The textbooks which are on them. Does it mean that real world problems is reduced to matrix operation in quantum computing using gates? Yeah, so that's how we try to solve problems. Does it mean that the real world problems is reduced to matrix operations in quantum computation using gates? Yeah. So any problem we have to solve, we need to map them. So the first hardest part is how efficiently you are mapping them. It can be a non-computed problem. Right? It can be a stock exchange problem. There is a lot of parameters. There is a lot of now every possibility has to be mapped to a quantum states. Now the quantum states can be created as superposition states, right? Now, which means that one parameter is affecting another one, like some file pair fall in one particular commodity can affect something else, right? So that's what when we mean mapping the problem. Now, if you map them all, then the operations on them has to be defined in some way, and matrix is result very efficiently. So that's where we do, and then the once the mapping is done, it's broken down into a matrix and computational problems. So I think there was an earlier question where, like, how if I want to solve a chemistry problem, should I learn a whole lot of chemistry and then apply quantum computers? No. If I have to solve a biology problem, should I do a lot of biology study and then implement a quantum algorithm? No. What we try to do is that either a chemistry problem or a biological problem, you break it down into some graph structure or some material, and then you forget about the chemistry or biology part of it. Then it becomes a matrix problem for you. And then you try to implement an algorithm for that and solve. And that's how people try to address some of these problems. Okay, how do someone validate and verify quantum outputs when classical algorithms are verification is infeasible? Okay, so this is a slightly right now. Someone validate and verify quantum outputs when classical algorithms or verification is infeasible. So this is more of at a small scale. You always try to verify whether your quantum systems are giving very efficiently, and classical algorithms also help you at that point. But the moment it is crossing the validation benchmarking is a very difficult problem, and people try to work with some quantum quantity verifiable methods, what we call, if it's entanglement based something, can I verify entanglement in that state? And can I verify any other quantum behavior or a subsystem measurement is what we call. You have an ancilla qubits, you observe, make partial measure, you make measurements on those ancilla bits and try to get some information on the quantum state. So there are few ways which people come out to validate, and they do also do a tomography, what we call a quantum state reconstruction, which involves various multiple measurements on a quantum state, and that does help to verify or validate quantum outputs compared to a classical outputs. Minimum coherence time one should maintain in order to avoid error occurrence. So actually, minimum what should be the minimum coherence time one should maintain? So now this is not what people have been trying to see is that they are trying to improve hardware to increase coherence time. Today, ion trap system has a reasonably good coherence time, so few microseconds. So which means that within that microseconds, you need to implement so many number of gates, or else error comes into the picture. So that's what people try to look at. More time, coherence time has increased quite a bit. In a photonic system, it's not coherence time most of the time, it is the coherence length, which means that up to what length photons remain coherent, and within that length, can I do this operation so that they don't become noisy. And that's how which people are. It's environment to a very good extent helps to increase coherence time. and that's what people are trying to control. There's nothing like on a minimum coherence time would be if I have to implement 4 gates, then I need to know what is the time required to implement those gates. If it's ion trap system, it's a pulse which has to laser pulse which has to be implemented, and what how quickly I can implement them, and that decides the minimum coherence time I would need. So, but the most of the time today, what people do is that they know what is the coherence time available in that system. They design quantum circuits to map that coherence time. Okay, which simulator do you suggest for hybrid classical evaluation of any problem? Now, this varies. Which simulator do you suggest for a hybrid quantum classical? So, which means that you need to have a quantum system and also a classical system with it, right? So, that depends on the algorithm. So there are certain algorithms, sometimes for a hybrid system, photonic hybrid quantum classical algorithms, variational algorithms. Photonics also are very good because you can actually do a lot of one-shot measurements on photonic system compared to superconducting or any of those things. But that again depends on the algorithm itself, right? If without knowing the problem, you can't decide on which hardware would be ideal. What does the phase pi matters? Why does the phase pi matters in this? Because when we try to take probability of mod square, the coefficient, okay, the phase pi matters. As I was telling you, when you are applying a sequence of operations, there's going to be a phase which comes after you do some operation. But if you're not making a measurement, phase will remain. But when you do another operations, you get one more phase. Now phases interfere. Phase plays an important role in interfering, and that can actually lead to constructive destructive interference. That is a very big thing, in quantum computers. If phases are not there, you are not going to get any constructive interference, constructive or destructive interference. When you don't have them, you don't have any quantum advantage. So phase in that way it plays an important role. Does this collapsing makes us lose any information during telecommunication? So collapsing, you do lose information, but what is important? I mean, whenever you make a measurement, you are losing information, which means that you are getting only partial information. But the way quantum operations or quantum systems are reconstructed is that you repeat experiment. But the moment you are repeating the experiment, then you get all the, every time it collapses randomly and you can reconstruct your quantum state. So you can retrieve a complete information of a quantum state by repeated experiment. So a single measurement will collapse, you lose information. But a sequence of measurements in different bases, what we call, which is like tomography. So you know this X-ray, or when you go for an MRI machines, do a tomography, which means that you try to see the information in various angles and you reconstruct your image. In the same way, a quantum state tomography is what we call. A quantum state measurement collapses and we lose, but we want to retrieve the whole of that state. So we do measurements in different bases, you reconstruct and you end up having a full information. So there is enough ways which people are developed to not to lose information. If I'm unable to retrieve the original state post superposition, how would I make it use? Yeah, that's what probably this answers. If I'm unable to retrieve the original state post superposition, how would I make it use? So post superposition, if you the quantum states are operations are unitary, you can actually go back and look at it. But if you're not making a measurement, then you changed you change the state, an inverse operation of that, you're going to get back a state. But if you're making a measurement, then you can do again the tomography and you can always retrieve an information. So it's not, the information is lost if you're doing a single shot measurement. That's what we mean. Right? In a 3D space, what would be the linear transformation preserved and not preserved? So 3D XYZ, when we're talking about Pauli matrices here, right? X rotation, Y rotation. I was talking about a sphere, which is called a block sphere, which represents a qubit. So the 3D space. So you can The linear transformation is a combination in X, Y, Z direction. So that's all preserved. So uh, it is preserved in 3 dimension. So in superposition of multi-qubit state, for a case of large n close to infinity, are all possible to the pen considered valid is the exhaustive combination of only takes some reference for a mathematical upper bound, and reality there is far fewer options since probability of continuous random variable takes on a specific value of zero. But I think they are talking about if you are having a multi-qubit state, the possible of 2 to the power of n considered values, and that's a huge configuration, and you may not be able to access all of them. Is what it's kind of, but that's not true. When you are trying to engineer, that's why we have gate operations. You can actually engineer operations on them to access all possible basis states. So it's not something which you'll not be able to access. It's difficult to do operations, but that's possible in principle. How do we detect entanglement between qubits? So there are specific ways to measure entanglement. We call a Bell's inequality test, for which actually a few years back they were also given Nobel Prize for coming up with this technique. So which means that you make some sequence of measurements and that gives some value more than two. If it gives more than two, less than 2 root 2, then it's called as entanglement. It's called violation of Bell's inequality. So any classical system can give only maximum value of 2, but if you get more than 2, then you can definitely establish that there is entanglement. There is also a quantum state tomography, which I described earlier, where if you reconstruct a density matrix, is what we call, we can calculate entanglement with that efficiently. So there are various ways to measure and detect, and people have at least 2 and 3 qubit systems, which very easily measurable. So that's one of the standard ways people validate their qubits operations, right? You have to actually, the moment you're claiming that you're building a quantum computers, you need to do operations, quantify your qubits, and you need to make those measurements, and you should show that there is entanglement being generated and that efficiency is so and so. Only then you can establish that you have a quantum computer, or even at smaller number of qubits. Gates are transformation matrix only. So can we apply same transformation matrix in classical computers just like we do in a transformation matrix either in classical computers or quantum computers are same, but when we talk about transformation matrix, I define transformation matrix to follow certain rules where the phases and normalities would come into the picture and unitary representation. That makes it unique for quantum mechanics, and not all transformation matrix will be suitable for it. So where classical computers would take up to have everything into that picture, and it won't have that unitary bounded. It's not bounded by the unitary, which is described in a quantum mechanics. What is meant by when we can erase a bit, which means that state 0 or state 1, that information is lost, but I don't know in what context I can relate it to quantum bit. I was talking about eraser, quantum eraser, which no, I didn't talk about quantum eraser, but this question about eraser bit is not very clear to me, so I can't answer. In no cloning theorem example, you are given 0 becomes 0 or the same as 1. So is it possible to get an additional Hilbert space using some operation? Also, it is also a reason that cloning is not possible. No, the linearity condition itself is a proof for it, right? If you say operation has to be linear, which means that it has to be linear at 0 level, it has to be linear at multi-qubit level. I know only then a linearity condition is valid, and that's what it would say here. You can prove it another way. What you can say is that if hypothetically we can say I can take a superposition state, an unknown state, alpha 0 plus beta 1, and then say there is some possibility that it's becoming 2 times of alpha 0 and beta 1. Now I need to come up with an operation which can do that. and you will never be able to come up with any unitary transformation which does that. So that itself is again a proof that okay, quantum mechanics operators should be unitary, and you can do. But you can use a lot of additional qubits and then do a lot of multi-qubit system, and you can do, you can actually copy. It's not copy. I would say you can state zero with some additional qubit. You can actually get that state, but that's a bit more involved. But what when we talk about no cloning, it's no cloning of that state, unknown state, onto another state. Why quantum computing needs vector algebra particularly? So because why quantum computation needs vector algebra particularly, as so there is a direction associated with it, with the quantum state representation. So that's what helps us to have phase and all of those things, which does not come with scalar representation. And because direction is associated with it, we need vector algebra. Vector algebra describes the space and Hilbert space which has direction associated with it. So I think there is quite a lot of questions going on. So I can probably stop at this point.
Yes, Professor. So
might be so.
Yeah, we'll take it up later. Take it up offline. Thanks, Professor. Thanks a lot. Thank you all the participants. So good night, Professor.
Yeah, good night. Thank you.
Let's meet tomorrow evening at 6 p.m.
Yeah, sure.
Yeah. Thank you, Professor. Thank you all the participants. Have a good day. Bye.
The recording has stopped.